Good morning, everyone. We shall continue our discussion on live variable analysis from the previous class. I shall briefly recap the definition of the live variable analysis problem. So we say at a program point P, that a variable V is live if there exists at least one path in the control flow graph of the function starting from the program P to the end program point or the exit basic block, along which the variable is used on the right hand side. For example, here you can see there are three paths starting from program point P to the end program point, and along the middle path, the variable V is neither on the LHS or on the RHS. So it doesn't matter. On the first path, on the leftmost path, you can see variable is occurring, but it is occurring on the left hand side. So it doesn't contribute to the liveness of the variable V at the program point P. But on the contrary, on the rightmost path, on the third path, variable V is occurring on the right hand side. And it is occurring on the right hand side before it is being defined along any point along this path. So this particular instruction contributes to the liveness of the variable V at the program point P. Similarly, if you take the rightmost example here, so again here the variable V is live at the program point P because there exists a path from P to the end program point. Along this path, the variable V is used before it is being defined. Variable V along this path, so along this path, variable V is used before it is defined. And in the example in the middle, so variable V is not live at the program point P because in both the paths it is occurring on the LHS. It is being defined before it is being used, if at all it is used. And in the middle path, it is not occurring either on the left, on the LHS or on the RHS. And the live variable analysis problem is to find out the set of variables that are live at different program points occurring in the control flow graph. This is the problem at hand. Let's try to get some intuition on how we can go about computing how we can go about arriving at an algorithm for live variable analysis. Let's consider a simple tuple. So we have this is program point P, and we have a tuple x is equal to y plus z, and this is program point P prime. So if we know the set of variables that are live at program point P prime, so if we know the set of variables that are live at program point P prime, then we can compute the set of variables that are live at the program point P. So the set of variables that are live at program point P is given as, we can easily see at program point P the variables y and z are live. So we will say y and z union all the variables that are live at the program point P prime minus x, because x is being defined here. So because of that, x cannot be live at the program point P. So it doesn't mean that x is not live at program point P prime. Like for example, at program point P prime, after program point P prime, if we have something like y is equal to x plus 1, then you can immediately see that x is live at the program point P prime, but it is not live at the program point P because it is being defined before it is being used at the instruction w is equal to x plus 1. Right? And this also takes care of the case, like for example, what if the instruction is this? What if the instruction is something like x is equal to x plus z and p prime is this? So this is perfectly all right, because if you see this uh, equation, if you see this relation, then you can see this will turn out to be xz. We know that x is live at, sorry, I made a small mistake here. So live of P is equal to this. So from this equation, we can see that, yeah, xz, so x is live at program point P. So you get, so what happens is, let's say if you consider this particular case, so at program point P prime, so there are many variables that are live along with x. And it gets, since x is occurring on the LHS in this particular tuple, x is equal to y plus z, it gets eliminated. But then it gets regenerated here, because we are including it in the first term here. So this is an important point to note, that at the program point P prime, so in the first case where if we have the tuple x is equal to y plus z, x is not live at the program point P, because it is live here, but it is not live at the program point P. But whereas in the second case, this is the second case. So this is case 1, this is case 2. So whereas in the second case, x is live here, and it is also live at the program point P, but for a different reason. The different reason is x is being used here. And if you check this equation, so these two, they correspond to this case 2, and this corresponds to case 1. So what happens is x and z are at the program point P, x and z are live. And if you look at the second term, so x gets killed. So x is live at the program point P prime, but it gets killed because x is occurring on the left hand side. But that is all right, because x is getting included in the liveness set because of its use via this term that is present here. So these two cases are very important cases for you to make a note and get a good intuition about. So once we know how to relate the live variables, a set of variables that are live between two consecutive program points, we can lift this logic and apply it at a basic block level. One thing I would like you to note here is the information is propagating upwards here or backwards. So if we know the liveness information at program point P prime, then we will know the liveness information at the program point P. So the information flow is in the backward direction. Great. So let's consider what happens within a basic block. So let's focus on basic block now. Yeah, let's say we start here. This is our basic block. And then, so we have the program point P1. Instruction I1 is present here. Program point P2. Instruction I2 is present here. Maybe I can use semicolon here. So on, so forth. program point pk, instruction ik, and the last program point is pk plus 1. So if we know for this is a basic block. So for this basic block, if we know the set of live variables at the program point pk plus 1, then what we can do is we can propagate this information upwards and compute the variables that are live at different program points within this basic block, including the program point p1. So that is how we can go about computation of live variable set at different points within a basic block, where the code is a straight line sequence of code. But let's say what happens if we go beyond basic blocks. So let's say we have another basic block here, and then we have another basic block here. So it is like this. Let's call this basic block as B1, this is B2, this is B3. And we can see the set of variables that are live at the program point which is ending the basic block B1. It consists of all the variables that are live at the beginning of basic block B2 and all the variables that are live at the beginning of basic block B3. So this idea, we express it by using this equation, that is relation, that is out of B1 is equal to in of B2 union in of B3. What is out of B1? Out of B1 is the set of variables that are live at the end of the basic block B1. And what is in of B2? In of B2 is a set of variables that are live at the beginning of basic block B2. And same is the case for basic block B3 too. And one thing we can note here that in of B2, that is set of variables that are live at the beginning of basic block B2, it is a function of set of variables that are live at the end of basic block B2. So what this function is, we will discover in a moment. Now let's see these. So we have another basic block here. Let's call it as basic block B4. And you can see we can relate the live variables across these basic blocks as follows. So the set of variables that are live at the basic block B3, it is equal to in of B4. And similarly, if you see, let me erase out of B2 is equal to in of B4. So if we know the variables that are live here, we can use that information. So if we know the variables that are live here, we can use that information to compute the variables that are live here, and we can use that information to compute the variables that are live here. Similarly, we can do the same here. Compute the variables that are live here, and then compute the variables that are live at the beginning of basic block B2. And if we know the variables that are live at the beginning of B2 and B3, we can use that information to compute the variables that are live at the end of the basic block B1, and we can propagate it up to compute the set of variables that are live at the beginning of basic block B1. So this is how the information is flowing backwards here. So let's say the successor basic block for B4 is the exit basic block. If the successor basic block for B4 is exit basic block, it is a good thing for us because exit is a boundary case, and we can safely assume that in of exit is equal to empty set. No variables are live in the exit basic block. So now that we know the information, now that we know the variables that are live at the beginning of the exit basic block, we can use this to propagate, to compute the variables that are live at the end of the basic block B4. We can propagate it further, and then we can see how information flows backwards. So from this, we can see that, and then in order to complete this picture, let's say this is the entry basic. So now we can see that we can solve the live variable analysis problem nicely. We take the control flow graph and we sort the basic blocks in the control flow graph in a topologically sorted order, and then we visit the basic blocks in the reverse topological sorted order. That is, we first start with exit basic block, and so we start with exit. We know how to compute in of exit because it's a boundary case. So from that, from there we go to before. So once we know how to compute the out and in sets of before, and once we compute uh, the live variables for the basic block before, then we can compute the live variable set for B2 and B3 in any order, it doesn't matter. And then after that, we go and compute the live variable set for the variable B1. And then after that, we get the live variable information for the entry basic. So this is reverse topological or reverse topological sorted order. So the story is kind of till this point looks very good, but there will be a there's a bit of catch, as you may have already expected. That is, in practice, control flow graph, they contain loops. So like, for example, here you may have a loop like this. That is, at the end of the basic block B3, there could be a condition. Depending upon whether the condition is true or false, the control flow can go to either basic block B4 or it can go to basic block B3. In which case, you can see this out of B3 function, it gets modified as out of B3 is equal to in of B4 union in of B3. So in order to compute out of B3, we need to know in of B3, but we know that in of B3, it is a function of out of B3. So there is a circular dependency here. So this leads to circular dependency. So how do we break this circular dependency? The way we break this circular dependency is by taking the approach of iterative fixed point algorithms, where we start with a certain initial estimate for these different basic blocks, uh, estimate of live variables, and then we keep improving our estimates. That is how we are going to break this circular dependence. Good. So now let's try to take a look at the formal algorithm for this. But before we take a look at the formal algorithm, I would like you to see what happens when we use pointers uh, in this in our program. All right. So let's consider, let's consider this instruction. So this is program point P, and we have something like x is equal to star P, and this is program point P. So the set of variables that are live at program point P is equal to the set of variables that are so that look at the set of variables that are live at the program point P prime minus x. So this is one term. So this is the second term that we have used in our previous relation. And there is another term. The another term is, so let's call it as points to P. Let me use PTR here so that it will be easy for you to. points to PTR. So what this points to PTR is set of all the variables which the pointer PTR can potentially point to. Okay? Like for example, let's take the case. So let's say if you, before the program point P, we have something like y is, we have something like PTR is equal to address of y, and this is another program point P double prime. So then at this point P, the set of variables which PTR can potentially point to, that is in this instruction, it is y, because so we are taking the address of the variable y here. Great. So, but this is a easy case where we are easily able to compute the set of variables to which the pointer variable potentially points to. But let's consider another case. Okay, so we have a control flow graph like this. If we have a control flow graph like this, and let's say we are, so we have something like PTR is equal to address of y. This is address of y, and here PTR is equal to address of z, and here we have x is equal to star PTR, and so this is program point P, this is program point P prime. So at this point, if you see, PTR can potentially point to variable y or variable z. So the points to set at this associated here, if you see, points to of PTR, it consists of variables y and z. So because of that, at program point P, we have to assume that either variable, both variables y and z are potentially live. This is how we handle pointers in our data flow analysis associated with live variables. If we don't do pointer analysis, so in order to compute these points to set, we may have to use very involved algorithms. We may have to invoke another data flow analysis module in order to compute these points to set. If we don't do these points to analysis, then what happens is when we try to process this, when we try to propagate information through this instruction x is equal to star PTR, the conservative information is PTR could be pointing to any of the variables in the program. Hence, we have to assume that all the variables are live at the program point. So the better the estimate that we can get, the better the estimate of points to set we get, the better will be the liveness information that we compute at the program point. So when we use pointers in our programs, when we use aliases in our programs, it becomes very important that we have a powerful points to analysis module, so that the analysis, the results that we get for liveness or other data flow analysis problems, it would be much more accurate. Great. So now let's go to, let's see, stop share, and sorry. Yeah. Are you able to see the desktop screen? I hope you are able to see the desktop.
Yes, sir.
And are you all with me here so far in the lecture? Doing
Yes, sir.
all right?
Yes, sir.
Good. So let's proceed then.
Sir, I had a doubt in the project. Can I ask it now or should I ask it after the lecture?
So the particular way in which we have approached the data flow analysis algorithm for live variables, we went to the program points and worked at that level. And it's a very good approach because when you start working with any data flow analysis problem, if you go to that level and see how the data flow analysis sets between two consecutive program points relate with each other, if you do that analysis, you get lots of interesting insight into that problem. And we can use that information to lift it up and come up with a algorithm which we would like to use in practice. So here, if you see in the live variable analysis, uh, let me use the annotation. So we define associated with every basic block, we define two sets. The first set is what is called as a gen set. So the gen set associated with a basic block is set of all variables x such that variable x is used before being defined in basic block B. Like for example, what it means is, let's say if this is a basic block, then if you have something like y is equal to x plus z and x is not occurring on the LHS in any of the tuples before this tuple, then x is what is called as an upwardly exposed variable, and this x belongs to the generator set, gen set. Okay, on the contrary, if x is occurring something like this, then x is no longer upwardly exposed because this definition is blocking this use of x. So the gen set contains all the upwardly exposed variables in the basic block, and you can easily compute this gen set by going through the basic block. You can just go through the basic block and check all the upwardly exposed variables. And the kill set consists of all the variables which are defined anywhere in the basic block. That is, they are occurring on the LHS somewhere in the basic block. So yeah, like for example, in this case, in this y is occurring on the LHS. So, so y belongs to the kill set of the basic block. So y could, at the same time, y could also be upwardly exposed. Like for example, you may have some statement like w is equal to y plus 1. So what happens is w belongs to the gen set. At the same time, w belongs to the, sorry, y belongs to the kill set also, because y is being defined in this basic. So what happens is, let's say if variable y is live at the end of this basic block, then it gets killed, okay, because of this definition. But what happens is it gets locally generated because it is being used in the basic block before it is being defined. So this is what happens. So this is a relationship between, if you see, gen b is a constant which is a function of the basic block, and similarly kill b is a constant which is just a function of the basic block. That is, we don't need to refer to rest of the control flow graph in order to compute the gen b and kill b sets. So you can just make a pass on the basic block and we can compute the gen b and kill b sets. But in order to compute the in B, we need to compute out B. But in order to compute out B, we need to know the aliveness information at other basic blocks. I'm just checking if I'm missing any points here. Yeah. So the other point I wanted to make is this, which I want to emphasize. We have seen it before. That is, this information flow is in the backward direction. So information is flowing in the backward direction. And how is the out B set of a basic block related with the liveness information and the rest of the basic blocks? We say that a variable is live at the end of this basic block B if it is live at the beginning of this basic block or at the beginning of this basic block or at any of the successor basic blocks of B. So out B is equal to union of insets of all the successor basic blocks. And this particular union that we are doing, this is what is called as a meet or confluence operator. So what we do is we take the control flow graph and we compute, we take the control flow graph and we compute we establish the relationship between the in B and out B sets of different basic blocks, and and across basic blocks also we set up relationship between their corresponding in B and out B sets. So this line summarizes how all the relations that we set up. For every basic block B, we have this relation. So where we relate the out B set and its in B set. And then the out B set of the basic block, it depends on the insets of the successor basic blocks. In the last class, we have seen that how we can represent liveness, live variable information using a bit vector. So this equation that we have expressed it here, we can express it equivalently in the form of a bit vector. Like for example, if there are 3 variables in the program, we can use a 3-bit vector. And if a variable, let's say the 3 variables are x, y, z, if the variable y is upwardly exposed, then we make this bit equal to 1, the other bits equal to 0. Similarly, if the variable, if you look at the kill set, if you look at, let's say if the variable x belongs to the kill set, then we'll make it equal to 1 and this equal to 0. So we can express this relationship using this bit vector representation. And what is the out of B? Out of B is you take the bit vectors of the insets of the successor basic blocks and you just OR them, logical OR them, then you get the outsets. So this information is very useful in practice because we can use bit vectors when you are doing data flow analysis in your in a real compiler. Let's see now. And as we have seen, if the control flow graph, if it doesn't contain any loops, then we can visit the basic blocks in the reverse topological sorted order, and we can compute all in B and out B sets. But all practical control flow graphs, they contain loops in them. So we have to use iterative fixed point algorithms, where we start with some estimate and we keep improving our estimate. So in this particular live variable analysis problem, the first step here is in of exit is empty set. So this is a boundary case. This is not an estimate. And for all other basic blocks, we estimate their initial sets to be null sets. So this is what is called as an underestimation. So we are starting with an underestimation. This is very important to note that we are starting with an underestimation. And in this while loop here, what we are doing is we visit different basic blocks in this while loop, and we keep improving our estimates. So for a basic block B, we use the current estimates of the insets of the successor basic blocks and improve its outset estimate. And then based on improved outset estimate, we improve its inset estimate, and we keep iterating like this until all the basic blocks, all the liveness sets, they converge. Let's try to understand this with the help of an example. So let's come here. Yeah. So here, this is our control flow graph uh, with no loops. So there are 4 basic blocks: B1, B2, B3, B4, and the initial approximation for different insets is empty sets. And so what do we do? So here, in this particular case, what we are doing is we are processing the basic blocks in starting with B1. So when we are computing out of B1, we use in of the entry. So this will be just a empty set, and we go to and then we try to uh, so we use the out B. So if you look at out of B1, so out of B1, let me make it clear. So we are trying to compute out of B1 in iteration 1.1 to start with. So when we want to compute out of B1, remember, out of B1 is nothing but union of in of B2 union in of B3. The current estimate of in of B2 and in of B3 is empty set. So what happens is the estimate for out of B1 also turns out to be empty. That is what is happening here. And then we use that information and we try to propagate that information upwards. And there are no locally generated live variables in this basic block B1. So because of that, in of B1 just remains the same. It's not going to improve. It will just remain the same. So now in iteration 1.2, we are visiting the basic block B2. And if you look at the basic block B2, again, what here out of B2, we try to update out of B2 by using the current estimate of in of B4. The current estimate of in of B4 is empty set. So out of B2 also remains the same. But when we propagate this information upwards, since the variable y is upwardly exposed, it has to be included in the inset. So this is the updated in of B2. The same is the case for basic block B3, which we are attending to in the iteration 1.3. And similarly, if you look at out of B4 is equal to in of exit, and in of exit is anyway null set. So we are good. But when we propagate this information upwards, we see that the variable z is upwardly exposed. So this is the set that we get. That in of B4 is equal to z and out of B4 is equal to empty set. Now when we go for, now in iteration 2.1, we revisit the basic block B1. And when we revisit the basic block B1, so you can see what happens. So B1 uses in of B2. B1 uses in of B2. This is in of B2. And it also uses in of B3. So in of B3 is this. In of B3 is this. So and it takes the union of it. So that's how out of B1 gets updated. And again, we try to propagate this information up, and there are no upwardly exposed variables in basic block B1. So in of B1 remains the same. So now let's go to basic block B2 in iteration 2.2. Again, so out of B2 depends on in of B4. You can see this depends on, it only depends on in of B4. The current estimate of in of B4 is Z. So it gets copied into out of B2. And we try to propagate this information upwards. In the process of propagating this information upwards, Z gets killed because it is defined in the basic block, but it is not regenerated again. So this is how we keep computing the in and out sets for different basic blocks. So there is a macro iteration and there is a micro iteration. In a macro iteration, we visit all the basic blocks. In a micro iteration, what is a micro iteration? When we are processing a basic block, let's call it as a micro iteration. So 1.1 is a micro iteration, 1.2 is a micro iteration. 1.3, 1.4 are micro iterations, and the whole of all these things put together, they form one micro iteration. So this macro iteration, so you can see if you go back to the algorithm for a moment. Clear. So this is the macro iteration. This is micro iteration. So after some point, what happens is you can see the estimates of the in and out sets at the end of the iteration, at the end of the macro iteration 2, and at the end of the macro iteration 3, they are the same. So at this point, what we do is we say that the algorithm has converged, and we will conclude the algorithm. So now let's see what happens if yeah, but obviously you may have noticed that we are processing the basic blocks in the, I wouldn't say wrong order, but it may not so favorable order, because it required 3 iterations for this algorithm to converge. But on the contrary, if we process these basic blocks in the reverse topological sorted order, that is, you process B4, B2, B3 followed by B1, then what happens is in the first iteration itself, we have the correct estimates of the in and out sets, and in the second iteration, we will get to know that we have converged. In fact, if we know that the graph doesn't have any loops, we don't even need to go for second iteration, because we know for sure, theoretically speaking, that the algorithm would have converged. So now let's take one more example. This is an example with loops. I will not go through this example. This example is it's easy, but there is a lot of detail here. All we are saying here is, like we are processing the basic blocks in this control flow graph in this order. In iteration 1.1, we are processing the basic block 5, followed by basic block 4, 3, 2, 1. So like, for example, when we are processing basic block B5, uh, so out of B5, if you see, out of B5, it is uh, obtained by taking in of B2 union, what do I say? Yeah, that's all. I think so. And it is it depends on in of B2. The current estimate of in of B2 is empty set. So that's what is happening here. That's what. But on the contrary, and then you take that out of B5, the current estimate of out of B5, and we propagate it backwards, and you can see A is an upwardly exposed variable. Because of that, A gets included in of B5. So you can follow these steps. These arrow marks indicate that out of B5 depends on in of B2. And similarly here, if you take in iteration 1.3, we are computing out of B3, and out of B3 depends on in of B4. Because of that, I kept an arrow mark here. And if you look at iteration 1.4, we are computing out of B2 to start with, and out of B2 depends on in of B5 and in of B4. So in of B5 and in of B4. So because of that, I kept an arrow mark here, in of B5 and in of B4, re-emphasizing here, and you take the union of them and you get this. So these arrow marks indicate that the dependencies, that this value depends on these values. And of course, within the same row, so in of B2 depends on out of B2. So because out of B2 we compute, and then we propagate that information upwards in the basic block. The same is true in all the cases. So So this one, this implicit dependency that in of B4, for example, depends on out of B4. It is not explicitly labeled, but you know it. Great. So here there are a couple of questions before we proceed further. The first question is, does this algorithm converge? So you can see one thing you can notice to argue about the convergence of this algorithm is all these in and out sets, they are monotonically increasing, and each of these sets, they contain variables, and the number of variables in your program, they are finite. So at some point, these sets cannot grow further. Like for example, if you see the estimates at the end of each macro iteration, these sets are all growing. At after some point, they cannot grow because the number of variables in your program are finite. And these sets are monotonically increasing. So if they are oscillating, then we get into trouble. But since they are monotonically increasing, so at some point they have to converge. This is the convergence argument. So in the last exam, in the midterm exam, I asked a question on what is the worst case number of iterations required for a fixed point algorithm to converge. So I want you to ask the similar question for this particular problem too, for this live variable analysis problem too. That is, what is the worst case number of iterations are required in order to converge? The second question is, we started with an under approximation. Is it necessary for us to start with an under approximation? What happens if you start with a over approximation? So let's see what happens if you start with a over approximation by taking a simple example. So if you see this example, so in this example so let's say there are these variables A, B, C, and there is one more variable T. Let's say T is a compiler generated temporary variable, and after applying some optimizations, the instructions which involve variable T, they got eliminated, but T as such is present in the scope of this function. And you can see, let's say if we start with an initial estimate instead of starting with an underestimate, if we start with a overestimate. If we start with an overestimate that we assume that all the variables are live, then what happens is you can see at out of B1 is equal to in of exit union in of B1. Out of B1 is equal to in of exit union U. In of B1. So in of exit is empty set, so it's not going to affect the estimate out of B1. But in of B1, we started with the overestimate ABCT. So what happens is in the first iteration, if you think in of exit is anyway empty set, you take the union and you have ABCT. So the estimate of out of B1, it will, after the first iteration, it will turn out to be ABCD. So now if you propagate this information upwards, then what you can see is A gets killed in the next iteration. This is, let's say, iteration I1. In iteration I2, what happens is out of B1, A gets killed, but then B and C are upwardly exposed. So they remain, and T is neither killed nor upwardly exposed. So the out of B1 set will be BC. And even if you iterate further, so T is going to remain because T is not there, so it's not going to get killed. It's not going to get killed. So if you start with an overestimate, you can see that you may end up including some variables which are not live otherwise. So we want to start with an underestimate, and we want to keep improving our estimate. And the key thing that you have to, that governs whether we should go for an overestimate or an underestimate is the meet operator. the meet operator or the confluence operator. In live variable analysis problem, the meet operator or the confluence operator is union. So whenever we have a meet operator as union, you want to start with an underestimate. You want to start with an underestimate. In order to reinforce this idea, there is one more example I would like you to analyze. So if you go here, so this is another example for and I want you to see how I want you to take it as an exercise problem, as a homework problem, and see what happens in this program. What happens if you start with an underestimate? What will be the set of live variables at different program points? And if you start with an overestimate, what will be the set of live variables at different program points? Overestimate means we assume not the beginning of all the basic blocks, all the variables are like. That is the overestimate. So this is a homework problem. I want you to think about it. This is a nice problem which when you try to do it, it improves your intuition. I'll formally post it as a homework problem today. Great. So now the next problem is available expressions analysis problem. We will study this available expressions analysis problem in the next class, and we conclude our discussion on data flow analysis in the next class. We compare and contrast the live variable analysis problem with the available expressions analysis problem and get a very good intuition about these two problems, and that would give an excellent introduction to data flow analysis module. That's all I have for today. So thank you. If you have any questions, you may ask.